At the end of the previous video, we saw that there are 308,915,776 possibilities for picking a 6-letter password, which sounds like a lot, but if you had a computer that could run through 1 million possibilities each second, it would take that computer just over 5 minutes to check all the possible passwords. For an 8-letter password, there are 208,827,064,576 possibilities, and it would take that same computer just over 58 hours to run through all the possibilities. But that's still something a computer could do if it was trying to crack your password. So to make it more secure, what if we force you to use a combination of lowercase letters and uppercase letters and digits and other special characters or symbols? So what if each one of those 8 letters or characters in your 8-letter password is any one of those 70 possible symbols? Any of the 26 lowercase letters or 26 uppercase letters or 10 digits or any of these 8 symbols? Now, if there are 70 possibilities for each individual letter or character in the password, the number of possible 8-letter passwords becomes 70 to the 8th power. 8 70s multiplied together. And if you multiply that out, it comes to 576,480,100,000,000 possibilities. So if somebody had a computer that could check 1 million possibilities per second, how long would it take them to run through all those possibilities? Over 18 years. So that's a big increase in security. Next example. Suppose 11 men and 9 women come to an audition for the lead roles in a play. How many ways could 1 man and 1 woman be selected? You got to pick one of those 11 men for the leading male role, and you got to pick one of those 9 women for the leading female role. Well, that would be 11 times 9, which is 99. 11 ways to make the first choice times 9 ways to make the second choice. Now, what if the roles weren't specifically for males or females? Anybody could play either one of those roles. How many ways could you just select 2 of the people who came to the audition? Well, there were 20 people, the 11 men plus the 9 women. So for the first role, you can pick any of those 20. And then for the second role, you can pick any of the other 19. Can't be the same person in both roles. So the number of ways you could select those 2 people would be 20 times 19, which is 380. Now, what if there are 20 roles available and 20 people come to the audition, so everybody's going to get a part? You just have to decide which person gets which role. Now, the number of ways you could do that is, well, that first role could go to any of the 20 people at the audition. Then the second role could go to any of the other 19 people. Then the next role could be given to any of the remaining 18, and so on. So altogether, you're going to be multiplying 20 times 19 times 18 times 17 times 16 times all the way down to when you get to that very last role, there's just one person left over who has to get that role. So if you multiply all those numbers together, you get, well, this really big number that starts with a 2 and then has 18 digits after that. That's a lot of ways. In how many ways could 6 books be arranged on a bookshelf? Like, you got these 6 books, you're going to put them all on a shelf, but you got to decide what order to put them in. how to arrange them, which one goes first, which one goes second, and so on. Well, think of this as making a sequence of choices. First, you have to choose which book goes first, which is going to be on the left. And there are 6 possibilities for how you make that decision. That could be any of the 6 books. Then once you've put the first book on the shelf, now you decide what book to put next, and you've got 5 ways of making that choice. Then there are 4 choices for what book goes next. Then you have 3 books left to choose from for what to put next. And then 2. And then whatever book you haven't put on the shelf yet, that's the one you got to put last. There's only one way of making that last choice. So altogether, that gives you 6 times 5 times 4 times 3 times 2 times 1, which is 720 different ways that those 6 books could be arranged. How many different ways can a deck of 52 cards be arranged? Well, same sort of idea. The first card, the one on top of the deck, could be any one of those 52. There's 52 possibilities for that. Then there's 51 possibilities for which card comes next, because it could be any of the other 51 cards besides the one that's on top. And then you got 50 possibilities for what's next, and then 49, and then all the way down to 1. So you'd be multiplying together all the numbers from 52 down to 1. And if you actually multiply that out, you get this really huge number. It's so big that I'm not going to try to write it all out. I'm just going to show it in scientific notation as approximately 8 times 10 to the 67th power. So if you did write that normally, it would be an 8 followed by 67 digits. So the next time you shuffle a deck of cards, the resulting arrangement is 1 out of 8 times 10 to the 67th possible arrangements. Now, these last examples, where we're talking about how many different orders a set of things, like a set of books or a deck of cards, could be in, these are called permutations. So a permutation is an arrangement of objects in a specific order. If we're saying how many orders or arrangements could these be in, we're saying how many permutations are possible. And turns out that the number of permutations of n objects, here that letter n just stands for how many there are, the number of permutations of that many objects taken all together, that is, the number of different orders they could be arranged in, is, well, you multiply together all the numbers from n down to 1. And there's a special notation or word for that. It's written with that number with an exclamation point after it, and it's pronounced factorial. So in exclamation point, when I see that, I would say in factorial. And that means all the numbers, all the whole numbers from 1 to n multiplied together. So, for example, 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1, which is 720. So, some number, exclamation point, is pronounced that number factorial, and it means to multiply together all the whole numbers from 1 up to that number, or from that number down to 1. Order doesn't matter when you're multiplying. And to make things work out consistently, and to have all the rules that work with factorials still work, we agree that 1 factorial is just 1. That makes sense. And 0 factorial is also 1. That doesn't make quite as much sense. You might have thought 0 factorial ought to be 0, but that would mess certain things up. So instead we say that if you ever meet a 0 factorial, that's going to be 1. So, for example, what's 9 factorial? Well, I can calculate that as 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And I get 362,880. Now, lots of calculators have the ability to do factorials for you. On some calculators, there's actually a button labeled in exclamation point or X exclamation point or something like that you can use to get factorials. On other calculators, you have to get it off of a menu. So on a graphing calculator like this one, like some version of a TI-83 or TI-84 or something like that, to calculate 9 factorial, I punch 9, and then I would go to the math menu, push the math button, and I want to select the PRB menu. PRB stands for, I guess, probability. And then I want the fourth thing on the list, which is the exclamation point for factorial. So 9 exclamation point, 9 factorial is 362,880. Okay, how about this example? You visit a city where 5 of your friends live, and you're trying to decide what order to visit them in. How many different possibilities are there? So this is a question about permutations, about how many orders those 5 friend visits could be in. Who's first, who's second, who's third, who's fourth, who's fifth? And the answer is 5 factorial, which would be 5 times 4 times 3 times 2 times 1, which comes out to 120. 5 times 4 would be 20, times 3 would be 60, times 2 would be 120, times 1 would still be 120. 5 possibilities for who you visit first, and then 4 possibilities for who you visit second, and then 3 choices for who you visit third, 2, and 1. Now, these next examples I first started using way back in the old days when there were, if you wanted to watch a movie, you would go down to your neighborhood video store and rent some movies on VHS cassettes or on DVDs and take them home and watch them and then bring them back the next day. So turn your mind back to the old days of video stores and imagine you go and get your entertainment for the evening. You rent 3 movies. You look at the shelves, you pick out 3 movies you think you want to watch, and you take them home. How many different orders could you watch them in? Well, this is another permutation question. That would be how many different orders those 3 movies could be watched in would be 3 factorial. 3 times 2 times 1, which comes out to 6. That's not too many, so here's the complete list. Here's the 6 different orders you could watch the movies in. First A, then B, then C, A, C, B, B, A, C, B, C, A, C, A, B, or C, B, A. If you're going to watch all 3 movies, it's got to be in one of those 6 orders. Now, what if you rent 5 movies, but you only have time to watch 3 of them? You bring home 5 DVDs or 5 VHS cassettes, and you get together with your significant other or your group of friends or whoever you're watching movies with, and you have to decide, well, we don't have time to watch all 5 of these. Which 3 are we going to watch? What are we going to watch first? What are we going to watch second? What are we going to watch third? Well, the number of possible ways to make that selection is 5 times 4 times 3, which is 60. 5 possibilities for which movie you watch first, times 4 possibilities for the second movie, times 3 possibilities for the third, and then that's the end. That's all you had time to watch. If you want to see what that list of 60 possibilities looks like, here they are. Here are all the ways of picking 3 out of those 5 movies. And this is an example of permutations where you have a certain number of objects to choose from, but you're only choosing some of them. So I'm going to end this video here and come back in the next video and talk more about this kind of situation.